right. Welcome honors students again. And academic? Or is this all honors?
Just honors.
Just honors. Welcome honors students. Got Mr. T here again to help us out with finding the relationship between velocity and time. This is not the same as distance and time. We just did distance and time. That was lab number 2. This is lab number 3, finding the relationship between velocity and time. And really, it's going to be average velocity and time. All right, so let's see what we got again. We've got a meter stick, ever present. Tape, ever present. What in the world is this? Mr. T, what's this called?
This is a dot timer.
Dot timer. Okay. What is this?
That's ticker tape.
Ticker tape. Okay, we'll be using that, I guess, as well. And then, that doesn't look like the cart that we already used that one. I think we'll be using this cart. Mr. T, what's this called?
This is a physics cart.
A physics cart. Pasco physics cart. Okay. When we come back, I think maybe we'll use that one too, just to have some fun. We're going to see how to do this lab a little bit.
All right, so we have the dot timer.
The dot timer, all right.
Now, before we plug it in, we're going to get the ticker tape set up to run through the dot timer. So let's, whoops, there we go. All right, so we start uncoiling the paper. This is just nice thin paper. What we're going to do, unroll a little bit. We're going to put it right through. These are actually staples. We're going to put them right through these staples. And just take it through like that.
Oh, Mr. T, I see what you're doing.
Right.
Are you illustrating one of the mistakes that many students make?
You got it.
Oh, what would typical students who've never seen this before do wrong?
Well, they would forget to put this purple disc on top of.
Oh, so we need to feed that tape underneath?
Absolutely.
Okay, so
let's go back and try this again. So
I'm glad you showed us that, Mr. T.
This is a carbon disc, and we're going to slide this right under, just like that. So now, what this dot timer is going to do, when you plug it in and turn it on, it's going to tap down on this carbon disc, and with the paper underneath the disc, it's going to leave little dots.
Cool. Mr. T, how many times per second does this dot timer time?
The dot timer will knock down 60 times per second.
60 times per second?
60 times per second.
Wow, that's pretty fast. Okay, so I guess that probably is something to write down. That sounds like an important thing to note.
Definitely important.
Dot timer will tick, whatever, come down, make a mark 60 times a second.
That's right.
Okay, so that's how we get it set up. Awesome.
All right, so we have our setup here. As we can see, we have the paper set up underneath the carbon disc. And in this case, we've attached it to our good old physics buggy that we used in lab number 1. So what we're going to do, we're going to turn this dot timer on. Well, first I'm going to plug it in. Now that we have everything set up, we can plug it in. There's a little switch here to turn it on. Once we have this going, we're going to turn the car on and let it go. And then we'll take a look. We'll come back and we'll take a look at the dots that it leaves on the ticker tape.
And the students, they're not going to be doing this one. We're just kind of trying to figure out how this dot timer works, right?
Exactly.
Because our students, the honor students, they're going to work with the Pasco physics card, but we kind of want to see how it works to begin with, right?
Yeah, and using
Okay.
something that you've already used before.
Should we do it?
Yeah, let's go.
All right, let's do it, Mr. T. I'm ready.
You ready?
Yes, sir.
All right, so I'm going to turn this on.
Oh, that's weird.
So 60 times per second.
60 times per second.
And here we go.
Okay, there it goes. Okay, and that was it.
All right.
Let's see what happened. So we got our marks. Let me see. Oh, I see them.
Really
I
close.
see them. Wow, that's hard to see with the focus, but oh yeah, I see the marks. Very cool. Okay, show me what you're doing, Mr. T.
All right, so we said earlier that this dot timer knocks down 60 times every second. So that means that every 61
60 spaces? Extra 60 spaces? Every 60 spaces is a second?
every 60 spaces is a second.
Yeah, intervals I guess we could call them, right?
Yeah, right. That's a good
So
way to
from
put
one
it.
dot to the next would be,
One interval. Right.
okay.
So what we can do to make it a little bit easier, instead of counting to 60 or counting 60 spaces, we can count tenths of a second.
Okay. How do we do that?
All right. So what we do is we count essentially 6 spaces. It's going to end up being 7 dots. So if we start at the beginning and we count 7 dots, 1, 2, 3, 4, 5, 6, 7. That's 6 spaces. And
Wait, is that 6 spaces or is that 7 spaces?
let's
You're
count.
illustrating another thing a student might do, aren't you?
Mm-hmm.
Ho, 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 ho.
1, 2 spaces, 3 spaces,
4,
4,
5,
5,
6 spaces.
7.
7 spaces.
There you go. See, this is why we
Yeah.
double check.
Okay.
So there's 6.
So let that be a lesson to all the honors students. Don't just blindly start counting. We got to actually look at the spaces, because if we just continue to count really quickly, we might make a mistake, and that'll throw off all our data. Because imagine if this initial one we had counted 7 spaces, even though it's 7 dots, but 6 spaces, then all of a sudden all the rest of the data would be off by 1 dot, and that would be just dangerous. Thank you for showing that.
Absolutely.
Showing that to us, Mr.
So be conscious of that. So what we can do, we can measure out this whole, we can measure out this entire dot paper in tenths of a second. When we have time measurements, we can then measure the actual distance that was traveled during each tenth of a second.
I am so confused, Mr. T. Could you help us figure that out one more time?
All right, so let's look at this one. So we know from the first dot to this blue line is 1/10 of a second.
Oh, that's 0.1 seconds?
0.1 seconds.
Okay, I got it. So every
All
6
right.
spaces is 0.1 seconds. That makes more
Absolutely.
sense. Now I understand why we did the whole 6 spaces business.
Right. So that's 1/10 of a second, 0.1 seconds.
Oh, that's my delta T.
That is your delta
Okay,
T.
now I got it.
Absolutely. Now, in that time frame, we can measure how far the car actually went.
Oh, that's delta D, isn't it?
That is delta D.
Okay.
So if we put the meter stick or ruler, we'll try and be careful with our measurement. We can take a look here and get a distance that the car traveled in 0.1 seconds. So it looks like we have, here's 2 centimeters, there's 3 centimeters, so we're just about 2.4 centimeters.
2.4. Now, don't students need to be really precise? Don't they have to actually
Absolutely.
estimate too? So we got 2.4.
Absolutely.
And I've got this thing called parallax going on because I'm a little off. If I were to look right on, we'd see that it would be, there it is, 2.4, but then we've got to have that estimator. So maybe,
Exactly.
what do you think, 2.45?
Yeah, I think that
Right,
looks
it
about,
goes right in between the 4 and the 5?
yes.
Okay, so 2.45 I see.
So to get the proper sig figs, we can estimate that last digit.
Okay,
So 2.45 centimeters.
is our displacement, and 0.1 seconds our time.
Right.
Okay, I think I know what we're going to do. Let's go ahead and do it on the paper, and we'll come back and check it out. All right, let's see what we got here. So we went through, there they are, and there are time intervals. It's hard to focus. Let's see. There, it's in focus. Okay. So I've got the displacements from one line to the next on each one of them. All right. I measured it all, and then let's see what Mr. T's got over here.
All right, so I've calculated all of these average velocities based on the delta D's and the delta T's.
Oh, how did you get those delta T's, Mr. T?
All right, so the delta T is the change in time
Change in time? From
So-
what?
from one dot to the next. Or I'm sorry, from each 6 dot separation.
Let's see. Oh, okay, I got it. From here to there is 0.1 seconds.
Exactly.
Oh, now I get it. Okay.
All right, so we measured the change in D between that time interval.
Okay.
Each of those time intervals is the same.
Oh, yeah, that
All
makes sense.
1/10 of a second.
Oh, and look, there's time. Is that the time that's going to be on the x-axis?
This
Yeah,
is
'cause
the x-axis.
Time's always on the x-axis. Not change in time. Time is always on the x-axis.
Correct.
I understand.
So we
So the
want the
first
total
interval is
time.
0.1, then next interval is 0.2. Okay, I understand.
All right. So here's the calculation for this last one I was doing. Average velocity is equal to delta D over delta T. We look here, delta D is 4.1 centimeters, and the change in time is 0.1 seconds. So when we do that out, we divide, and we end up with 41.0 centimeters per second. We'll place that in our table. 41.0. The units are already up in the header.
I like how you done that.
So we don't
That's
need
great.
to do it. So here, how about this last one? So we'll do one final. And as we do this, we're going to do it along, writing out the variables. All right, so we have change in displacement, 4.20 centimeters divided by the change in time, 0.1 seconds. We divide that out, we end up with 42.0 centimeters per second. Put that up on our table.
Oh, that's
There we
really,
go.
look at that. So the average velocity, looks like for the car, kind of goes from 23.5 to 31, or through 33, and then 38, and then it stays pretty much at 40 the entire time. And that's what we saw on the ticker tape. The ticker tape is, all the intervals are about the same distance apart. That means that the average velocity is about the same the entire time for the red cart. Interesting. Okay, well, we kind of understand how the dot tape timer works. I think it's going to be time to use that Pasco cart. So, all right, let us do it. Mr. T.
All right, here we are. So now we are moving on to the nice blue physics cart. We have our setup on a ramp. We have our dot timer. We have the paper underneath the carbon disc.
Nice.
All right. So here I am. I'm going to plug it in. We're going to get this all set up. Get your car in place.
Okay. I guess I'll hold it so that way it doesn't go anywhere when you turn it on, and then after it starts, then I'll let it go.
Okay. All right. So I'm going to turn it on, and we're just going to let it go, and it's going to do its thing. All right.
Okay.
There we go.
All right.
Pretty good.
Cool.
There we go.
There are our dots.
You can see our dots. Now we just have to do some measurements. Mark off tenths of a second.
Oh, that's right. How many? 6 spaces?
6 spaces is
Okay.
1/10 of a second. And then we can measure each of those tenths of a second, and we have a distance. We have a time associated with it.
All right. We'll be back. All right. Here we go. There are our little markings. Every 6 dots. It seems like they're getting further and further away from one another. And if we look, that's 11.2 centimeters distance, 12.89, 14.46. There we go. 16.8. Wow, they're definitely getting spaced out a lot. I think Mr. T has made a table for us.
All right, so here's our table. We have our total time elapsed that we measured over there. Here's your delta T between each set of lines, 1/10 of a second.
Oh, yeah, that's right.
Here's our delta D, our displacement. So we have this down there in centimeters.
Oh, yeah, that's for each set of lines. The spacing is, this one's 11.21, then 12.8. Yeah, that's what I was just noticing over there.
Exactly.
Okay.
The spacing was getting bigger as we went down for the same amount of time.
Mm-hmm.
From that, just like we did before with the physics buggy, we calculated the average velocity. So you can take a look at the calculation that we did before, but here is the average velocity.
And we have these in centimeters per second.
Centimeters per second.
Nice.
Right.
Okay, so we got our data table.
All right, and
Ooh,
We
Mr.
went
T,
ahead.
that is a fantastic graph.
yeah, that's looking pretty sharp here.
Oh,
So,
man. Would you like to do the honors?
Sure. All right. First of all, before I do that,
Let's
take a
turn
look.
this sideways so we can see it really nice.
Good parts of this graph. We have a title.
Ooh, yeah.
We have axis labels with
Mhm.
units, and it's nice and big. Always nice to have a
Excellent,
big
yeah.
graph, taking up a lot of space. So, of course, we're going to draw a best fit line. I'm going to start at our 0, 0 point at the origin and do our best to hit this right through the middle of our data. And I'd say right about in there looks pretty good.
Yeah, that's nice. Is there any way to go continue with that all the way through the paper?
All the way up top?
Yeah, it
Oh,
looks like
sure.
we might go through a intersection up top there. I'm not positive, but...
All right.
Oh, it's close. It's close.
Mhm.
I was hoping. Okay. Mr. T, what do you think happened there? That's interesting.
That's a good question. I think
Like we had increasing velocity, increasing velocity, increasing velocity, and then it just kind of stayed the same.
so these 2 points probably present some good questions. It's at the end of the data, so
I wonder what that means in real life, what happened at the very end.
well, I think they can observe their car going down the ramp and make some conclusions off of that.
Yes, sir. Yes, sir. So, what now?
Now we analyze. Now we start taking a look at this and seeing what some conclusions we can draw.
Right, and I guess the slope is going to be the relationship between average velocity and time, which I'm pretty sure the students know what that is now.
That's right.
Cool.
Yeah.
All right. Mr. T, thank you for showing us how to do this.
No problem.
We're signing off. See you tomorrow. Right.
Trying to get in, find you through the cracks, find you